name is Sharifah. My name is Sharifah. I am your MC for today's lecture. So we are very honored to have one of a prominent researcher in the area of printable and flexible electronics in Malaysia, Dr. Asrulnizam bin Abdul Manaf. For your kind information as well, this lecture is co-organized by the IEEE EDS together with us at the Center of Printable Electronics. So before we begin, there are a few housekeeping announcements. We would like to kindly remind everyone to please ensure your microphones are muted if you are not speaking to avoid any disruptions throughout the talk. If you have any questions for the speaker, just type it in the chat box or you can ask your questions at the end of the talk. Okay, we thank you for your cooperation. Right, before I call Dr. Asrul to the stage, I wish to take just 10 minutes, okay, just 10 minutes of your time to give an introduction of CPE and also an introduction of the IEEE EDS. All right, I hope you can see my slide. Can you see my slide?
Yeah.
Okay, thank you. So just very quickly, Center of Printable Electronics CPE was established in 2017, but we are fully operational only in 2019. Only started in 2019. It's being led by Professor IR Dr. Nohayati Soin as its director. We've quite got a lean members. We only have 7 personnel. We've got one postdoctoral visitor, Dr. Hanim from UiTM. We've got one postdoctoral research associate, which is Dr. Hazwan, which is also linked with CRES and MIDA, right? And we've got 2 support staff. We've got Hafiz and Puan Hidayah. Thank you again for this. Without Puan Hidayah and without Encik Hafiz, it's hard to move actually. So thank you for you all. And we've got 2 full-time students. I see now we've got Azwa here. Azwa is our PhD student. She's inside this meeting as well. Thank you, Azwa, for coming. So the objective of this talk, of our CPE, is basically we look into innovative solution for wearable healthcare application. So we look into healthcare, but slowly we are also moving into other branches as well. We are exploring agriculture and PPE. And these are our key research focuses. We are looking into sensors, electronics, RF, which is the electronics interfacing with the sensor. We're looking at energy harvesting, looking at solar cells, as well as materials and processes. So we've got some current projects, and these are our equipments. If you are interested to collaborate with us, please do email us at cope@um.edu.my. If you are interested in using our facilities, yes, you can also email us. So next, I want to do some overview for the IEEE EDS. So EDS is it promotes electronic devices for the betterment of the humanity, and it fosters professional growth of our members. So these are the field of interest within EDS. So if you feel that you are within the studies of research, yes, please do become a member of IEEE EDS. So it's not at all expensive. It's just $20 and USD $20 per year, which is less than 100 ringgit, and students can receive even more discounted price, which is about 10 USD. So these are the benefits of joining IEEE EDS. You can get free access to the webinars, technical contents for the top IEEE journals. You can network with all the EDS members. We can help you to network with other international IEEE members. You can get access to cash awards, recognition. For instance, we have the student fellowship programs. You can get fundings for not just research, technical research, but also for humanitarian projects and many more. So these are the EDS publications, okay, that EDS sponsor. We are within region 10 out of 10, which is here. Okay, there are in total 220 chapters in IEEE EDS, and we are the only one in Malaysia. This is a picture of the members in IEEE EDS. I think this was taken before COVID. We've got some prominent lecturers inside IEEE EDS. We've got Prof. Naushad from Uniten, we've got Prof. Zahirul from IIUM, we've got Prof. Nahayati, we've got Prof. Suzy from UKM. This is our current chair, Dr. Sabirin from UITM. We also hold a lot of numerous lecture series and DL programs. For instance, in August, we did DL Distinguished Lecture programs with Professor De Souza from Sheffield University and Professor Rais Zadeh from the US. We also are known for our Let's Talk series, okay, where in this is kind of like a forum. It's quite interesting. The attractive thing about it is that we invite industry speakers as well, not just academic speakers, and we talk about different topics every month, different topics within the electronic devices scope every month. So yes, please join us. This is quite open. It's open to public. We also are very active in our humanity activities. For instance, we did some donation drive for COVID, and then we also developed some face shields for the students. And I think just recently, we did a ceramah kesederhan, the awareness talk, I think last week. We are also quite active in our STEM activities. This is being led by Dr. Aliza and Dr. Azwin from IIUM. So this is a good thing about being in the IEEE. You are also exposed with other, you also meet with other people from outside your own universities. So yeah, these are the activities that we did. And only recently, just last Saturday, Dr. Azwin and Dr. Aliza did a training with the students to use Raspberry Pi. So these are pictures again taken before COVID. We are quite recognized by other IEEE chapters. We are being awarded with the Outstanding Chapter in 2018 and 2017, and these are some of our awards. We are also co-organized some conferences only last 2 years back in 2020 and 2021. We did a virtual conference. Hopefully in 2022, we can do a hybrid conference in Langkawi. So that's ICSE. So I hope you guys can, everyone can send some your current work, to our upcoming conference. We also acknowledge women in the engineering. So we did, this was done in March, earlier this year. We did a forum to talk about the women's in engineering. So this is Assoc Med. So yeah, you can visit us at Facebook, YouTube, and Instagram to see our activities. Again, please do join us at IEEE EDS. We welcome your participation so that we can collaborate and join our activities. So, right, let's dive into the talk. So Dr. Azrul, while you are sharing your PowerPoint presentation, you can share it now. Okay. So while Dr. Asrul is sharing his screen, I'd like to give a brief biodata of our speaker today. So Dr. Asrulnizam Abdul Manaf received his BE and ME degrees in Electrical and Electronics Engineering from Toyohashi University of Technology in Japan in 2001 and 2005 respectively, and PhD degree in Engineering from the Department of Applied Physics, School of Fundamental Science and Technology at Keio University, Japan in 2009. He was an electrical engineer with Toyo Memory Technologies in Berhad, Malaysia. Since 2009, he has been with USM as a senior lecturer, and he was promoted to an associate professor in 2015. He has authored and co-authored more than 60 international technical journal or conference papers. He was a recipient of several innovation awards at national and international invention competition. He currently has 2 patent filings for DNA sensor and CMOS-based tunable inductor. His current research interest includes development of microfluidic-based DNA sensor integrated with CMOS circuitry, miniaturized of fluidic-based inclination sensor, bio-inspired-based microfluidic acoustic, pressure and flow sensor for underwater system, microfluidic-based memristor, microfluidic-based tunable inductor, microfluidic thermoelectric generator-based energy harvesting, graphene-based transistor, and micro 3D fabrication. So since 2016, he has been an academic staff with the Collaborative Microelectronic Design Excellence Center, CDEC, in USM. So the floor is yours, Dr. Asrul.
Assalamualaikum and very good morning to all the participants, and then first I would like thanks to chairperson for a kindly introductions, and also thanks to the centers of the Printable Electronics University Malaya, and also the IEEE EDS, and then for these invitations. Okay, so today I will share with all of you what our current research specific on the printable electronics that we already started in since 2017, the 2017 or the 2016. So today I will focus on the lab on flexible stretchable circuit board for wearable medical applications. So before I start, give me about 5 minutes to introduce our centers and my research group. So that what our current topic or the current research that did in my group. So like explained by a chairperson, so I'm from University Science Malaysia, and then I belong to Collaborative Microelectronic Design Excellence Center. That is one of the center of excellence under Senate University Science Malaysia. So our center we established on the 10th November 2005, and then that under MOF, the Ministry of Finance, and then started operate in the 2007 under University Science Malaysia. So currently we have 70 staff. So we have the 4 academic staff and 7 research officers, and the 4 assistant engineers and 2 admin staff, and then currently we have 15 postgraduate students that be supervised by 4 academic staff at CDEX. So our location is at a main island at Penang. So if you have been in Penang, we just located at Bukit Jambul. So if you have been stay in the Equatorial Hotel, so it's just about 5 minutes walking from Equatorial Hotel, and then from the airport Penang about 15 minutes from the airport. So that is our office. So before that our center at the engineering campus, and then 2013 so we moved to the Bukit Jambul, so that we at the new USM campus we call as a sign at USM. So in terms of the industrial linkages, we also, I think the Prof Hayati already familiar with us, and also Prof Dr. Jaharia from UKM also, that we also have the MPW program, the multi-program wafer, so that we offer services, that means to all universities and then SME companies, so to access our EDA tools that are available in our servers, that can do a tap out at the Silterra through a multi-program wafer program. So recently, we have signed NDA with TSMC and also the ST Micro. So that for tap out for the chip fabrications. Right. So if you have a chance came to Penang, please visit us and at our campus at top hill at the hill. So that sea view. So that as a sign at USM campus. Okay, so let I focus on my group. So actually, my group, so we are focused on the integrated circuit and sensor system. So what our focus in my group, so we are focused on the two areas. First on the sensor development and also on the silicon-based CMOS circuitry. So that when we have a sensors, so that we be able to integrate with a CMOS, but it's not towards to the monolithic chip, we towards to the heterogeneous integrations. So that's why for a sensors, so we apply two technologies. First, as a printable technologies. The second is the silicon micro machining technologies. So, but today we more focus how the our our research. That means our activity, the research activities, how we implement the printable technologies, and then how we do the sensors development. So currently in our group, we only focus on the four type of the sensing mechanisms. So we focus on the electrochemical based sensing mechanisms and FET based sensing mechanism, the acoustic and the maps, the only the four type of a sensing principle we focus, and then we develop the sensor based on the four type of the sensing principle using printable technologies that we are focused on the flexible and stretchable substrate. So then when we develop the sensors, so that we do the monolith, not we do as a hybrid integration. I call as a hybrid integration because we don't have the facility to have the monolithic chip integration. So actually the circuit we fabricate separately using the CMOS or the silicon process, so that we do the hybrid integration on our printed circuit board. So that like the FR4, and also we have explore on the TPU and also the polyvinyl alcohol, and then to develop the sensor. So this is one of the examples that done in my group. So we have the EC sensors, then we do the modification on the electrode. So this one fabricated in our lab. So we fabricate the 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 circuit. That means we have the microcontrollers, and then we have the temperature sensors. That this substrate is a TPU. It's a Teflon polyurethane. So mean this substrate not only bendable but can stretchable. That's why I will talk later how we do the optimization as a circuit trace if we want to apply to on the stretchable substrate. So this one of the that of course, so we integrate with the microfluidic that towards to any specific applications that you using the PDMS, the polydimethylsiloxane. So this is what the roughly about my group. So that we focus on the sensors, and my team we have the others academic. So we have two more academics. So where they are focused on the CMOS circuitry. So like the ADC, DAC, and also the power amplifier, PMUIC. So towards to by combining the sensors and that circuit, we try to we develop what we call as the IoT physical device. So the one a system for the system on chip lah. So but it's a hybrid integrations. So today I really appreciate to the Prof Nohayati group, and that to invite us and to invite me to share what our current activity that I in a specific area on the printable electronics, then how I apply on those type of the sensors. So this is what I want to touch today. So the printable, stretchable electronic devices, but specific on the medical applications. So this is what the outline for today. So I will explain the motivation how we focus on the lab on printed circuit board. some I use in term lab on the printed flexible. I use some I use the lab on the FH, the F, the P, the flexible, the FPCB, right? So the lab on flexible printed circuit board. So that, but today I just give some idea in our group how we focus on the develop the a few sensors, PS using the electrochemical sensing, using a printable electronic, how we develop the PS sensors and also the strain sensors that with a specific application for like for a wound monitoring. And then how we give you some as how we explore in terms of the substrate selection, how we do the selection, the criteria into the printing technique. A lot of the printing technique that available in the current technology, we have the inkjet base, we have the screen printed base, and then we have a lot of few type, but there is they have the criteria that you have to match with type of your application and your ink condition. That how we explore by a collaboration with the School of Material Sciences, a Prof Marati, and also the Prof Zulkifli from USM, how they are how their group that developed for us the traceable quantitative ink, because our group we only focus on sensors. We not expert in the chemistry and the ink formulations. That's why this project, this printable, we work with the chemistry and also with the some we also purchase from the overseas the ink. All right, so that when we have the ink, so we just do the sensor design and do proceed on the fabrication based on our design requirement. So and then we touch a little bit some outcome, some output in work on the stretchable connective ink with the Prof Zulkifli from the School of Material Sciences and also Prof Al Mariati from School of Material Sciences that we apply in our strain sensors, right? And then the last before I end, so I will explain some work that how we apply the to prove the workable printed circuit board not on the FR4. So if you're so all of you familiar with the printed circuit board, but mainly for the FR4, the flammable retardant 4. But if you are going to design a circuit on the stretchable substrate, mean you have the it's not rigid subset. So that means a few criteria that you have to consider. So that I will give some examples and then how we did in my group. So that we out with the summaries of my talk. Okay, so I think Prof Nohayati and I think all of you already familiar with some they call as the lab on chip, right? The lab on chip mean how they are towards to the diagnosis, right? Towards to have to simplify the diagnosis system, and then it's in 1890 when the MEMS technology, the microelectronic mechanism, the MEMS technology is explored in the 1980. A lot of sensors is come out. I mean the small pressure sensors that will be able to have the small the micro valve. So this is a type of the advancements of semiconductors fabrication, so that they have the lab on chip. So that means how they have technologies, how be able to miniaturize the functions of the lab on one substrate. But in our group, because we try to make it what is the affordable technologies. I mean, what is the simple technology? Because if you rely on the lab on chip, we need go to a lot of complex of fabrication tools such as like the sputtering, the evaporation. Of course, you have to have a good lithography. That means based on to miniature. That means for a pattern fabrication. So that's why in our group, we still using a term lab, but we rephrase not lab on chip, but the lab on printed circuit board. But we try to explore the various type of the printed circuit board, from the FR4, the flammable retardant for substrate. There is a normal rigid substrate that the common use in any circuit board. But we also explore in the new subset that towards to not only bendable but also can be stretchable, right? So mean on that board, so we can have sensing the functioning. So mean we can have the microfluidic for to flow the samples, and that they come to the reaction chamber or any sensing region, and then to make the detection. And that we had previously integration with our silicon interface circuit, and then to do the amplifications. So by having that technologies, that we can minimize, because by integrate the flexible and with a micro with a channel, so that means we can minimize the volume of the sample of volume can minimize. So when the volume can reduce, so that we can make it the system can be a fast detection. That what. And also when the volume is reduced, mean we also can reduce the waste to the environment. So that the motivations of the development for the lab on printed circuit board, right? So towards to that technologies, what we focus in my group recently, we are focused about the smart Bandaid. So how we can develop a smart Bandaid system, right? So what the problem with a current smart Bandaid? So the current wound management. So when you have injury, when you have a wound, they may have a injury, for example, like the diabetes patients. So after they done surgery, they mean they have some have a wound. That mean you have to, the doctor have monitor your the wound condition. That means you have to clean the wound, and that so after. But the current bandage, right? So when they attach on your wound, so the doctor cannot get objectively data in the real time. So normally, so doctor will advise you, okay, please come to the next week, and then to hospital, and then they will open up and they can see, oh, I mean they have to do a cleaning again, and then do some antibiotic treatment, and then they will paste again your wound. Based on some literature review, when they have to the doctor will replace a new bandage, right? So like I have a case like in my mother, the last 5 years, they have an injury on the L4 and 5, and then they have a treatment. That means the operation. So every week have to come to the clinic, to the hospital, and then to replace a new that bandage. One bandage is cost about 100 something, 150 ringgit something. So that for about 3 months. That means they have to do the monitoring. So but some papers, so we did some review. So when the doctor is open up the bandage, they also can affect, they call as the second injury to the wound. That's why they will affect your prolonged wound, right? Your that because the lacking of the objectively measured data in the real time. So that's why from this motivation, with how we can able to do some a new evolution of bandage, but not only a bandage, but be able to give the objectively a data or not, that wound condition is still okay. That means no need to change the bandage, right? So for example, we need the objectively a data on the wound condition. right? So from that, so that we can have the closed loop system. So we do some literature. We did some literature review in our group. So that is that we found a good papers from the Matthew is Brown. That they are this group published in a frontier in bioengineering and biotechnologies. So from that paper, we found so that mean they have a few parameters that we consider your wound condition. So mean the pH condition at the wound area and the oxygen level at a wound condition and also the temperatures. And also some data, they also have a strain analysis of the tissue, right? So from that data, so maybe it's a possibility by having using the printable technologies, how we be able to develop the pH sensors so that we can know, oh, so this what is the conditions of their wound. So this is a normal scale, right? So that is what the pH, that is from their study. So that is the range of the pH. So mean if your pH, the wound pH is more alkalic, so mean it's easier to the bacteria to grow. That how to reduce back a healthy pH. So mean they need we give this a proper the amount of dose antibiotic. From that paper, some they are what a system can give a right amount of the antibiotic. That means to do a treatment to what that is to work to what we call as a precision medicine. So mean the precision. So mean we can have the right using a correct data. Mean the objectively a data so that we can know what the amount of the dose like the antibiotic can deliver to the wound so that can be a precise control of the wound condition, right? So there is a few the parameters, but in our group we still not focus on that oxygen level yet. So we focus on the pH sensors development and also the temperature sensors development. That means it's that towards to that applications. So when we go through a few so that mean so we know that is our design specification for our pH. So this is our the resolutions of our temperature sensors. So by knowing that what the design spec, that means the parameter what we call is a sensing parameters. So that how we going to develop the sensor. Of course must be using a, a right bandage as our substrate, right? So that the second thing, so it means towards to that, what is the material that available? That means for a pH. So because my group, we are the electrochemical sensing principle. That the focus in our group. That's why how we using the electrochemical sensing principles to act, that means to develop the pH sensors using the three working electrodes technique. So that we go through a few they did some paper from Hardy et al. They studied variations of the sensing materials for a pH and also the pH, the range of pH and also the sensitivity. So then because that we find one, and then the second, why you want to handle with any the bio, that mean this the pH must direct attached to the skin, that means to the wound. So it means you have to ensure the biocompatibility of the material, right? So that's why so we have the G, and then we find the GO there. But the good that is going from the next equation. So it should be that is the good that if 57 is most a good sensitivity. So that means we can see it's the range from 4 to 9 at least. So that means we can see that GO can go to the 4 to 10, and then but the sensitivity is still lower compared to the others. So that's why also that how we can apply the GO and then do some ink formulation on the graphene oxide as a sensing membrane for the pH sensors. So that's some some they we start so that a study on the sensors development and also the design specification towards to that, like the wound monitoring applications. So from that, and then now we come to how to do the selections of the materials. That means the substrate itself, because we try to make it okay. Hopefully one day attached to the skin, how to make it to avoid the inconvenience to the patients. So that we go through some the paper from the Rogers et al. That's a very top that we consider as the founder of the Printable Electronics group. So they did a good study in terms of the conformal conditions, right? So there is some the substrate thickness, right? So I mean, if you see these diagrams, you also can have a detail on that paper. Sciences is published 2011. So that is the thickness. If your substrate thickness is 400 micrometers, is 400 micrometers, and then you can see they still have a gap. So how the analogy of 400 micrometer is such as like our silicon wafer thickness. So if the current silicon wafer thickness is about the 400 to 700 micrometers, so that the roughly the thickness of wafer. Mean that the skin the image of the skin structures, and then you can see that it still have a gap. It's not really adapt the good attachment on the skin. So this a group they going to study in 100 micrometer, and then you can see they have the improvement but still have a gap. They cannot follow the conformal structure of the skin, so of the body skin. And then they towards to the 36 micrometers, and then they did improvement, but after they reduced to 5 micrometer thickness, and they can see a very good conformal on the skin structures lah. So but right now the latest is the latest thickness that did by the group from from Yamaguchi universities. They have they presented 1 micrometer thickness, the 1 micrometer thickness substrate. On top of that, so they have the array of the OTFT, the transistors, the array of transistors. So this is 2011. So that's why. And then the other criteria, so if you have to more sensitive, and then you can make it a good conformance on your skin, the other criteria for the selection substrate, not only the flexible, not only the stretchable, but also the thickness of the substrate, right? So that is, but it is need some a good chemistry lah, the good chemist or any the material expert, how they did a study, that mean in terms of the substrate formation, right? So this is the second. So what during that our group, so that we all mean that we know. So in that that one of the criteria is some the thickness. So it's some I think that is a famous picture. So if you did some printable electronics, so that they have some that is a normal pictures that we capture, we take, and then we put in our slide as our that we call as the trend, the innovations in the printable electronics. And then is some from that continue from this part, and then what the other issue. So what the other issue that studied by the Prof Somaya, this is from the Prof Somaya group at the Tokyo University. They also considered as a good as a founders and good researchers in the printable electronics. So this is our the silicon rubber, and then there is a paraline 1 micrometer. So their group actually I will not explain detail on that material. So they have a nanomesh conductors. This is a gold electrode. So they do the evaporations that electrode on the polyvinyl alcohol. So the polyvinyl alcohol we consider as a water soluble materials, right? So they printed the pattern of gold electrode on on the PVA, and then they use water. I mean the heat treatment. So the PVA we remove. So when the PVA is removed, so the pattern straight away can be attached on your skin. So what they are studied there, so if the other technique, so mean the issue on the skin effect. So mean so they so mean this area, so it's a fully attached. So that mean they not any like the air gap for the skin to breathe. That what they are mentioned in that paper. So mean so by having that nanomesh electrode, so mean they have the gap, so the skin to breathe, they naturally breathe, so that can be effect the the effect of the skin. So that's why in the group they come out a new material that the subset they call is a polyvinyl alcohol. So the polyvinyl alcohol, there is a water soluble material, so that when you can print it first on that, and then you can put on your skin, and then you can use a heat treatment or the water spray. So that PVA we remove, only the pattern can be attached on the body. So that also in my group. So based on a few literature review, so in our group we did a few substrate. So we using a few substrate to develop the sensors, such as like the polyvinyl alcohol, and then the TPU, of course the PET pol and the polyamide, and also the latest we also some did on the on gelatin as subset. And then you can see there is a data. So by having the nanomesh electrodes, so mean they no inflammation, right? So mean they no inflammations is compared to the other subset like the silicon and paraline, right? So so this is the a few the thickness lah, the a few subset that available in our group. So by do the design specification, the sensing parameters, and then that we have to consider also the substrate thickness. So based on the application, the second, I mean how we can do the printing. That mean the make it our subset can be a flexible. So all can be a stretchable. Right. So this a few some study done a very top research group, and so from of course from the Illinois, from the Tokyo University, the Post America. So these a few the evaluations of the evaluations of the system, and the evaluation of the printable electronic accessible devices. So if you go through, actually we have a three type. That means the three method to make it our subset, to make it our flexible devices. So I just quick. So the first they call as a deterministic composite. What mean deterministic composite? Mean we need the substrate. We have the substrate. On top of the substrate, we deposit with the thin film, but we make it the thin film like the thin film make it like the geometrical. Like if you're familiar with a Japan like concept of origami paper, so that mean they have a pattern like a pattern like origami, the geometrical. So that's why when you stress that, so the origami we also the stress lah. So that can be the concept, but you need the fabrication tools. I mean to do the pattern, the patterning to form the like this image. So the structures. So that mean when like when you stress, so the spring. I mean the geometrical structure will be stressed. So that one of the method. The second method they call as a random composite. What is a random composite? Because when you want to have the stretchable, right? So I mean you want to develop the sensor. It mean must be conductive, right? But of course, when you talk about the conductive, a metal is a conductive, but metal is not polymer, because when it's not have a polymer, they cannot stretch. But the polymer is an insulator, it's not conductive, right? That's why one of the methods, I mean, they do some ink formulation, some composite formulation. That means by advancement in the gold nanoparticles, the silver nanoparticles, and then they do the mixing. I mean, we have to ink how the ink formulation we using the PDMS like polymer or the PPS pedal, but we can mix with the conductive particle, but must to ensure the homogeneous mixing, so that can be have the conductive polymer. So that can, one you stress, is also can be conduct the electricity, right? So and then the others, the third technique they call as the liquid metal, the intrinsically stretchable. So what that there is some uniqueness. I mean, we need to have the micro channels that we insert the liquid metal in the micro channels lah. So that means one, so the fluid movement we consider the stretchability, right? So but in our group, so we focus on the second technique. So that's why we explore on the printable technologies, how we have worked with the group from the chemistry school of the material expert, how they can help us to do the ink formulation, but the conductive polymer ink formulation, but can have a highly conductivity, so as a baseline to a copper thread, the copper, like similar to the PCB that commonly used in our printed circuit board. But of course, to have a similar 10 power 6 like the PCB is a really difficult. So we try at least 10 power 4. That is a sufficient based on application. If you want to do the antenna or any the inductive, it must have a highly conductive materials, the highly conductive ink. Right? So that so that so by select the random composite two, of course we need to have a few printing technique that available lah. So that means we have the inkjet printing technique and the eject dispense like the concept of 3D printing, right? So that means they have so each printer, of course, they have a different type of the ink character. The most important is the ink viscosity, right? So if you use the inkjet, the viscosity is too light compared to the screen printing. Screen printing, that we need like a paste, like the ink is like a paste, like a conductive paste. So you have to match. You have to match with your type of a printer, and then you have to match with the properties of your ink. That's why if you buy if you are purchased from the overseas the ink, and then you have to ensure the properties must be matched with your type inject. So this is a few viscosity that you have to consider. Basically, like it cannot be a paste, that is can be a so they cannot, that mean the nozzle we cannot operate properly. So if you use the screen printed, so it means the ink must be like a paste conditions, right? So in our group, so in my group, so generally we have a two type of the printers that we focus on the inkjet, and then we also have the screen printing. I mean, to start the explorations in our printable electronics. So why with the inkjet? Inkjet, if you compare to the screen, the inkjet, if you can minimize the ink, that means you can avoid the waste. But the very challenge lah. So from our experience, I work with a few group from the ink formulation. Is very challenged to do the ink formulation for the inkjet based printing, right? Compared to the screen printing. And then the second, so you have to consider also the cure temperatures, because when you buy the printer, they have a spec on the heater. That means the cure temperature. So I mean the ink that you buy must be right, must be at the range of the printer cure lah. So it mean so if your ink, the cure temperature is too slow, so that can avoid the that can reduce the pattern resolutions, right? So mean how we do how we mesh the printing, the printing type must be matched with the type of the ink. So how we choose the ink criteria, ink viscosity, of course the line width, the line thickness, and also the uniformity. Normally when the ink come out, that means they will start to cure from a center to the edge. The center to the edge. Some that mean they have some uniformity between the center and between the edge lah, right? So that's why if you see the inject that the thickness, because this is a the inkjet base, so that is the thickness is 0.1 to 1 micrometer thickness, but the screen printing the thickness is too thick, right? That's why based on your applications, so that you have to choose the right printing, then based on your sensors, I mean your device application. So this good preview done by Tacos Meyer. So they did a review but specific on the TFT, the thin film transistors. Right. So in our group, so that's what we are focused. So now we are going to develop the heater, the micro heater. So mean the temperature sensors and also the pH sensors. But the oscillation we use what the available in the market, the commercial sensors. So the concept is, so when they detect the temperature is highest, or so the heater will heat up or cool the heater heat up, so that can be a localized temperatures. So that we use the flexible wires and then connect to the MCU, the microcontroller. You need to do the processing. So today, today talk, I just focus on few printable for the PAs and using the electrochemical sensor. So that's what we the whole system that we imaging the dream, the illustrations of for the good the smart Bandaid. So mean when they detect the conditions, the wound is a bad or the alkalic, so mean they need have the storage of amount of the antibiotic can deliver the localized deliver to the wound condition, so that can be make it your wound can be a fast healing, right? And then, so why they need the oxygen? Because from there I studied, so the oxygen is needed. That means to ensure the cell have a sufficient nutrient. That means to healing. That means to heal, to do the healing process. So through that, so mean we have to do the selection of the substrate, and then you have to do the selections of the printer must match with the conditions, and also the thickness substrate also be in the considerations before you proceed on the any application for the medical devices. So this some our work a few, I think the last 3 years in 2017, right? So that we work with the one of the Jabil. So that what they are going to uh, uh, we want to have the conductive polymer. That means the conductive ink, but not only conductive, and also not only bendable, but stretchable. So if you're familiar with any the PCB fabrication, we have the polyamide, but the polyamide they can only flexible, but only can flexible, can bendable, but cannot stretchable, right? So if my experience, so if you have one layer, if you have the 4 layer, 6 layer, at the end the flexible be a rigid, right? So that is some limitation. Of course, the thickness the most important concern if you want to maintain as a stretchable and the flexible devices. So now how we do develop, and then for example, like your substrate is a flexible, but your ink is a metal ink. You use the silver ink. The silver ink is a more common and established ink that you can available with the cheaper cost lah. The silver ink, but the silver ink, they're not flexible, they're not stretchable. So mean when you are printed, when you are printed the silver ink on the stretchable substrate, so when you stress, so the ink will appear off because they have a compress and tensioning a problem between the substrate and the thin film. So mean if you are going to apply for the stretchable application, so the ink also must be able to stretch without having a peel off problem. So from that, so we at that time, so we did some study because we using the PDMS. The PDMS is a polymer because my group are familiar with the PDM because we started earlier the PDM in our microfluidic that we buy the PDM we bought from the signature. So that the company, so that, but it's a polymer, mean it's a insulator, it's not conductive. So that time, so they do some study on a mixing lah, on the mixing with a silver nanoparticles with the ink, and then they do the homogeneous mixing. So this some cross-sectional view, the SM image, so we can say that have that's a the green color is a filler. So that means the silver nano particles, but you can see they have a gap. So when they have a gap, so that can reduce the conduct activity. And then, so that means there has a last gap between the flake and between the particles and the other particles. So I mean, if we can reduce the gap, so I mean you can improve in terms of the conductivity. So that is some at that time. So they do some mix how to reduce the gap. So that so some change the silver nanoparticles using the silver flake, the silver flake, and then that can minimize the particle to the particle contact that do the development is the stretchable conductive ink using on the polymer. So this at that time 2017. So there is some they use the strengths so that they do that the PDMS, so that the ink there is a mixing between the PDMS in the silver nano but the silver flake. So that means they good in terms of if you flake also mean the intensity is the same. So that means it's a good conductive. And then the others work, so that the others we also have the this is with a Prof Marathi group. So that we did, so this the strain sensors. So how to make it the sensitive, how to make it a very sensitive strain. So that we so the same, so that we using the PDMS. So the PDMS that we mix the we do the play around with the ratio of the silver nanoparticles, right? So this is some so this is so my one of our PhD students. So that work the collaboration with the School of Materials, so that they handle so she already graduated this year and also back to Myanmar, right? So that is so we do some so at that time, so by assist by the from the School of Material Prof Marathi group, so that they do a lot of the ink formulation lah. The ink formulation depend on the percentage. So there's a nanowire, so they with a few PDMS, so that that is some if with the EcoFlat, so that can be as a capacity is more the insulators. So that is there's a mix between the PDMS. So actually that is the ratio. So we change from the 0.1, 0.15, 0.2, 0.2, and then 0.25, 0.25, and then 0.3. So that is the percentage of loading, the filler loading, right? To get hard, I mean to do the in term to improve the conduct activity. So by having that structures, so actually we did some good the gauge factors, and the strength range can be up to a 70%, at 70%. But the latest the strength, I mean the accessibility. I think the last week we had one keynote talk from the Prof. Is go to 1,000 percentage traceability. Is very good. So we only a 70%. So that is some the of course you need to play around lah with the material properties. So this is what we tested. Then we do some the twisting analysis, see how the robustness of the ink, and then that we also did some hysteresis studies, and then see some studies on the we put on our finger, and then we can see how they're sensitive to check the finger. That means to detect the finger motion, right? So that is and then the others. So we also do some the fabrications, and that technique that we of course towards to smart bandage. So that we bought that bandage from pharmacies. So this that we do a printed on the CNT ink. So that is some our first test. I mean the test on the conduct activities, and also we also some tested this just play around. That means we tested also on the gelatin. Then we want to see how the addition between the ink and the vesture of the substrate, right? So and that we also done develop the PS sensors. So we publish on the sensors material, but we still suffer in terms of the sensitivity. So this is still ongoing to that on the formulation, the ink formulations. And then the others in our group also, we are trying to make it like the water-based ink, mean to for a biocompatible process. So that is the others. We have the carbon black. So we do the printing on the carbon black. So the sensors that from the ink. So that is a printable technologies. So that is we printed at our laboratories. And also that the my group also we also have some exploration on the FET devices for the any sensors application. Right? If they want our the crash grind, so that we do some salmonella detection. So we that our own the telemet, our own custom made printed the own custom made on the electrochemical sensors. So we prove the formulations. I mean gold, and then next we do the RGO. But we've done a first tested on the PCB, that we going to replace a few substrate lah. That means to do the salmonella detection using the electrochemical sensor. So that we design, that is our own design for EC sensors. So and then the same we also do a tested on the others work. So in our group, because we also do a testing on the heavy metals using the PCB, the printed circuit board, that we can have take some the data on the on the heavy metal detection, and then we reach the LOD until to 32 part per billion. So this is some the integrations with microfluidic, now still in ongoing with my PhD students, that we try to make it the flexible, the stretchable. So that on the microfluidic integrations. So this is our lab. So that's one of the examples. So that is the screen printing base. So that is that we bought from the Volterra, and then we also do a few tested on the multiple subset. So like I give so at the so and then this is our the board factory. So this is for the inject base. So the inject base, so that is that we are printed on the TPU. So this is a TPU subset. So we attach the TPU on our rigid subset. So after we done the fabrication and then we peel off that TPU from the platform. That means from the rigid platform. And then the others work, we also have study the possibility. That means to develop a circuit trace for a printed circuit board. So this is a normal the Gerber file is if you do the design on the printed circuit board, the rigid FR4. And then you can see here, if you design on the PCB, that means that is a normal. That means they have the sub edge corner. That can be the sub edge corner. That can be the sub edge corner. So that can be the sub edge corner. But when you apply on the stretchable, mean your subset will be stressed. So mean they have the possibility this sub will be break, right? So mean from that what we do some work with a school of mechanical and then they do some stress analysis. So that they from the stress analysis we can see so mean with a sub edge so that more stress that easier to break. That's why we work with ongoing. That means how we can have the standard fabrication. That means the standard fabrication like if you design the IC. I mean we have the process the PDK file, the process design kit file. So I mean the same. So if we apply on the stretchable, so I mean we need to study how the curving. Right, so that mean that is what we design the conventional PCB the Gerber file, but we need to have a curving. Also the same for the pad. And the pad also that we cannot have like the sub edge corner. That's why we have a design with a because we so that we have a the pad also there. So like this, it means they have the curving, the curve. So that we do some study what we call as the PDK file, the process design kit technology for the stretchable design for the circuit design. So this some our tested. So mean we can see here. So this our the PDMS. So that is the server ink. So that we have the LED to turn on and can see that the power is supplied. So this is the microcontroller, the MCU, and then to control the temperature monitoring. So that we can see here. So that when I attach the head, when we attach with the finger here, then we can see the changes of the temperatures lah, right? But of course they have the ambient temperatures. That means they have not a right in. So that means we need so the reading is done, and then mean the MCU can work properly. Mean the MCU can flow the current rating about 16 milliampere. So this is what we prove the surface mounted the SMT. I mean on the with a small component, with a larger component, and then with a medium size of the component to prove for the stretchable the stretchable printed circuit board, right? So that before that actually to come to get that outcome a lot of so because the second problem when you did with the printed circuit board, that means the SMT, of course we need the paste, that means the conductive paste, right? So the conductive paste also must be the stretchable conductive paste. So if you have a rigid paste, mean that your like we have a needle, that means we have a pin, the foot pin of the your MCU. So I mean we use stress So the pace also will be open up. So that means your component will be pay off. Right? That a few some we go through lah. So the challenge. So this is what we did for the stretchable. So I mean the flexible circuitry on the temperature sensors. This one of that from Jabil. So that they come on the was original on 2016. The flexible the printed circuit board. So this is what I will do some printing. So that is on the PVA. So this is on the polyamide. So that is on our Bandaid. So this is on the J13. So that the Bandaid we bought from the pharmacy. So made it pure transparent. And then but we still suffer to have a good the very thin film of the substrate. So that is the PVA. So that's on the TPU, the Teflon polyurethane. So as summary, so we done some implementations of the printed technologies to develop the pH sensors and also the strength sensors, and then we tested with the stretchable conductive ink, and also we do some proof study on the development, the process design kit for the printed stretchable the stretchable printed circuit board. And they made that for with a surface mountain the SMT. Then next we are going to have the microfluidics technologies on top of the few sensors to work to the medical applications. So this is the announcement from my group. So that from my from our collaborators and also from our group and then all the student staff and also some application for this work. Thank you.
Thank you. Thank you, Dr. Asrul. Thank you, Dr. Asrul, for the very engaging talk. You have shared with us not only your active research at USM, but you had also given us a comprehensive overview of current published work by others. So providing us some insight, some ideas on what we can do for printable research. So thank you, Dr. Asrul, for that. So now I open for questions. So if you have any questions, you can type into the chat box or you can open your mic and ask directly. Here I've got in the chat box, I've got 3 questions.
Yeah.
Okay, Dr. Liana asking, what is the minimum line size that this 3D printer can print?
Okay, for in our case, because I use inkjet and the print screen, the minimum 600 micrometer.
600.
Yeah, 600 micrometer right now. That what we do the optimize. So it means the gap also not less than 600 micrometer. So if we design a few technique, a few pattern is less than 600. If less than 600 micrometer, they have the overlap because that based on what our lab, what our available printed in my lab lah. So that we only can do 600 micrometer line.
Okay.
Yeah. Because we still difficulties because the optimizations of the heating, the cure temperatures. The problem is what are different between us and the others like the top guy. I mean like the Tokyo instance, they create their own printer, their own ink. So it means their ink already optimized with their fabricated printer. In our case, we buy the printer. We buy the printer and then we buy the ink. So that a lot of the mismatch lah between the ink formulation and also the printer. So that the case like there is a normal if you buy the Epson printer and then you only can buy the Epson ink, right? That is a you if you have a Epson printer, you cannot buy the ink from brothers. But in the current printable electronics in my group, because we don't have the expertise to build the printer, so we also buy the printer from the outsource, I mean from the overseas. But we also have so say some ink for example some printer some company they only have a few ink limitation. That means like so. But if you want to tailor in your sensors design, you need have the uniqueness of your ink, right? unique ink. That's why this difficulties lah. That means to do the mismatch between the printer and the ink formulation. But if you go through is the papers from that Somaya, they done, so there is some their ink that there is an injection 30 to 50 micrometer line width can go. But of course, if you have a right ink that optimal with the right printers, if they inject, so that the line width that you can go. So like a screen print, that is like the maximum that can go. But must have ensure right viscosity, right cure temperatures that with your printer that you available in your lab lah. So but the inject that the resolution lah.
Okay. Next question. From your experience, which substrate and type of ink should we best avoid due to poor adhesion or brittleness? What type?
Krypton.
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 Substrate.
The substrate is a really difficult about the additions. So that's why in my lab we focus on the TPU and also the PVA. The easiest substrate is a polyimide. That's already established. The polyimide you can do any the experiment with a copper and also with a silver. The most established ink is a silver ink. It's most established ink. That can easier. So that's why we also in my lab we also open the services. If anyone to do a printing, but we offer for a silver. But for the carbon, like in our business, we have a carbon ink, we have the stretchable conductive ink. We not offer to services. That's only in a research mode. But the silver is already established lah.
Okay. And then for your smart bandage, you directly printed on the cotton bandage, is that right?
Yeah.
So any specific issues you face when printing on textile?
Of course. The first about the connectivity.
Connectivity,
Yeah. The connectivity, because when you have a cotton, that's why when we do the printing, that's why we cannot. The good is with a single layer should have connectivity. No, we need multiple layer. Here with the one layer, but one layer still have a first. They not enough. That's why some that cases we do about the 20 layer.
Okay.
To do the painting, so that can be the more that others the filter. That's why. So if the single layer can be enough conductive, that good lah, because that you can lower down your cost and you simplify the process. But in our experience, so that we need the multiple layers to have a good conductivity. Yeah.
Okay. Okay, from Ms. Azwar. Thank you, Doctor, for your talk. You mentioned earlier that ink formulation of inkjet printer is difficult compared to screen printer.
Yeah.
Can you share a bit? What are the challenges?
Okay. So that just from my I just say what we facing the problem lah, right? So let I see some. So that our okay. So that the inkjet. So that the inkjet based printer. Of course, the inkjet based printer, the really the critical is the viscosity. Mean you cannot do a paste, right? And then they have a nozzles. And then the problem is, so when you want to have but if you want to just print silver, fine, should be no problem. But if you want to tailor-make your ink to be a polymer, but must be conductive. When you have a polymer, but must be conductive, you have to add with a particles, the silver flake. Because from that, we have to tailor-made in terms of the nozzles because they can have a clog the nozzle. That the first we facing. So a lot when we pay off when we put in the cartridge. So actually how we did in my lab. So actually we bought a lot of the free cartridge, and in this cartridge they have a span. So we have to learn how the mechanism of the cartridge span. So mean the first when we they need a high volume mass of the ink. So because the span, so in this cartridge they have a span. So when you fill in the liquid, so some liquid the span we absorb a few of liquid. Right, so mean they have do right calculation between the volume of cartridge and the apps how your ink can absorb to that span lah. So it means the cartridge is too complex is compared to the screen print. The screen print is easier because you need to have a mesh. You just design a mesh and then you just screen print. But the problem is the screen print compared to inkjet, the screen print you can waste the ink. But here you can minimize the volume. But the cartridge is too complex in terms of the span component that you have to write volume of the amount of the ink. If not, that your ink will be dry, right? And then the second, the size of nozzle must be considered with your particle size. That means your silver particle size, right? And then also the viscosity and also the heater, the cure. Because the inkjet, the ink is too is not viscous. It's not too viscosity. That's why if your cure is too slow, so that can be merged is others. So there are a few some we have a facing problem like about the cartridge cloth, and then about the optimization of the cure temperatures, and also that they avoid us about the print resolutions. Yeah.
Okay, thank you, Dr. Asrul. If CPE has any problems, I hope you can ask you to help. You have a very extensive experience in this. Okay, last question. If you have someone asking whether you have a position for postdoc.
Postdoc. Actually, we just end the postdoc application. The last the deadline already finished, and then the new postdoc will come on the October lah. So right now we don't have any vacancy yet lah for a postdoc. Already fulfilled with 2 postdoc lah in my groups. Yep.
I see. If you do have position, do you do advertising? How do you advertise your? Maybe some people want.
Yeah. Actually, we do the advertise on our Facebook for a CDEC for our center Facebook and also our website lah for call for the postdoc. The last submission is on the on the June, and then that means the result already done lah. The last on the September, and then the new postdoc we start to register on the October. Yeah.
Okay, so if people who interested to join Dr. Asrul, please look at the FB, the social media.
Our social media for my centers on the social media on our centers, and also some on our website lah. Yeah.
Okay, so I'll stop the program now. But before that, I would like to present Dr. Asrul a certificate of appreciation. There's another question. Sorry.
Yeah.
One more question. Last one. Maximum which concentration can be used in case of RGO?
Mean the concentrations, constant we in our lab we not tested with the RGO, we use GO. So the GO that the letter that we did with my student is the 10 about the 10 micrometers that the micromolar. So that what we did lah. So that of course we have studied also the RGO. So the problem is the RGO. So we are still study on the mean they need like the the to reduce GO from that our partner lah, that mean collaborator, they need some the toxicity. That's why some they study how using the Assoc something like that. That can be the all the water soluble GO lah for ink. So is it you mean the concentrations of RGO or the viscosity of the RGO or the concentration of the RGO that we use in our sensors?
I believe so. It's a question. Okay, thank you, Ahmad.
Yes.
Okay. So before I end, I'd like to share. The Asrul, can you unshare your screen?
Yeah.
Yes. So, sorry. So thank you, Dr. Asrul. This is a CJ penghargaan appreciation from us.
Thank you. Yeah.
Thank you for your time.
Yeah.
For the lecture.
Thank
And
you.
we will share this sorry everyone. We will share the recording of the session in IEEE YouTube channel.
Okay.
If you to look back at the lecture, we will post it there.
Yeah.
Okay.
Oh, I see Prof.
Prof. Burhan.
Bandaid,
Yeah,
our Sifu here.
Yes, our Sifu. Everyone's Sifu is here. Yeah. Prof. Burhan is here. So before we finish, can I take a picture? If everyone can open their camera.
Yep.
So I can take a picture. And yes, thank you. Okay, thank you. Anyone else? Okay. Yeah. We'll wait for everyone to open the camera. Okay, so okay. All right. Okay, so I think I'll take a picture now. Okay. Good. Even I didn't take. Sorry. All right. Okay. Thank you. Thank you everyone for coming.
Yeah. Thank you for
thanks, Dr. Asrul.
Thank you for invitation.
Thanks, Dr. Asrulnizam.
Thank you.
Okay, thank you also to Prof. Burhan, my Sifu, Prof. Burhan. So I've started my MEMS, my MEMS research since 2001 with Professor Burhanuddin from IMAN. So Sifu of IMAN, and I was one of the graduate PhD students, first batch from IMAN. Prof, thank you very much. So now I'm leading the Center of Printable of Electronics. I'm still new, baby, not even I think 5 years. So thank you for all participants for the great talk done by Dr. Asrulnizam. So of course later we will be having
Prof.
again the collaborative research. So we have to support.
Before I continue my PhD in Japan to 2006, actually I met Prof.
Dr. Asrulnizam, insyaAllah.
At the IMANS. So he advised me about the microfluidic lah. At that time, I think it's 2005. 2005. At the IMANS, That continue my PhD lah.
Yes. Yes, Prof Burhan is everyone's Sifu, not just yours. Okay. Okay, thank you everyone. Okay, thank you for coming. Okay, bye.
Thank you. Bye. Stay
Assalamualaikum.
safe. Take care. Bye bye.
Bye bye.
Bye.
Thank you.
Thank you. Bye.